Hi everyone, my name is Gustavo Mastroianni. I'm a lead network designer at BT. I work there for designing complex projects for Wi-Fi and mobility. And today I'm going to present you how Wi-Fi works, the Wi-Fi fundamentals, so you can design your network better and understand how Wi-Fi works. I'm also a member of the Mobility Brazil community, which here we do and we spread the word about the correct way how to deploy Wi-Fi and how the Wi-Fi works. We just did the first conference 2 weeks ago. It was a blast. Everyone liked it. So now I'm going to show you how Wi-Fi works and give you some design tips on how can we design Wi-Fi and make it better. All right. So now the first thing is, what does Wi-Fi stand for? Everyone thinks that Wi-Fi stands for wireless fidelity, but it actually doesn't mean anything. Okay, so there is a whole story behind it. As you can see, you can Google it and go to this website, Community Aruba Networks. There is a whole story about behind it, but don't think that Wi-Fi means wireless fidelity. It means nothing. It's just a brand. Okay. So next, we are going to talk about the 2.4 gigahertz band for Wi-Fi. So today we have a total of 14 channels, but the 14th channel is only available in Japan. And when we are designing a Wi-Fi network based on 2.4 gigahertz band, we only have 3 non-overlapping channels, and these non-overlapping channels would be channel number 1, number 6, and number 11. On the top picture, you can see for the channels and how the channel is, the pattern of the channel. So you can see that this is for 802.11b, and the figure below, it is for 802.11g, and then because it's OFDM. So we only have 2.4 gigahertz band to be used on a 802.11b, G, and N. We have 3 non-overlapping channels, 1, 6, and 11, each one of them with a 20 megahertz channel width. Channels should not be bounded. Enterprise class devices like Cisco, Aruba, Aerohive, Ruckus, it doesn't allow to bound channels on the 2.4 gigahertz band. Usually, small office, home office devices allow that to happen, but it's not a best practice because you end up not having interfering on other networks that are your neighboring networks, and that's not the best practice that we should use. So when you are designing for a 2.4 gigahertz band, you keep in mind that we can't use 40 megahertz channel width. It's only 20 megahertz channel width, so we can have at least all the 3 non-overlapping channels. This band is also a high interference prone band, so high interference from Wi-Fi and non-Wi-Fi devices like microwave ovens, baby monitors, Bluetooth devices, and headset devices. So you can always have some kind of interference that is not good for your network. So the main drive today is to move away from the 2.4 gigahertz band and go to the 5 gigahertz band. Now talking about the 5 gigahertz band, We have the Uni 1, which has 4 channels, 420 megahertz channels. Uni 2, we also have 420 megahertz channels. Uni 2 extended, which we have 12 channels, but 3 of them are weather radar. So sometimes it's not advised to be used. We should not use sometimes if it's near an airport. And for Uni 3, we also have 4 channels, 420 megahertz channels, and the ISM, we only have 1. So for 802.11a and n, we have 21 usable channels. Each one of them is 20 megahertz channel width. Keep in mind that I'm not considering the weather radar channels. For only for 802.11n, we can bound these channels and use 9 channels of each, 40 megahertz channel width each. For 802.11ac, we got another channel. We got the channel 144. So we have 22 usable channels with 20 megahertz channel width, 10 usable bonded channels for 40 megahertz channel width, 5 usable channels, bonded channels with 80 megahertz channel width, and 1 usable channel, bonded channel for 160 megahertz channel width. As you can see, channel 144, only 802.11ac devices can see it. So if you when you're planning and design your network, nowadays, only if you have control of all devices and you are sure that that only 802.11ac devices are associating to your network, then you can use it. But if you have no 802.11ac devices on your network, these devices will not see the channel 144, and there will be a hole in your network that it will not be usable for no 802.11ac devices. And for the Uni 2 and Uni 2 extended band channel bands, they are DFS channels. So they are dynamic. DFS stands for dynamic frequency selection. Radars operate on these frequencies. So every time an AP that is using one of these channels between 52 and 144, every time the AP hears a radar hit, it moves away from the channel for 30 minutes. After this period, it will return back to the previous channel that it was assigned. So for example, I'm assigned to, the AP is assigned to channel 100. If there is any radar hit on this channel, it will move away from unknown DFS channel, for example, 149 or 153 from Uni 3. And then after 30 minutes, it will move back to the channel 100. So if you don't know which frequency is each channel, you can do a simple calculation. So the center frequency calculation is 5,000, which means the 5,000 megahertz, plus 5 times the channel number. Example given should be 5,000 plus 5 times 36. Then we get the channel 5,180 megahertz. Okay, and you can do that calculation for each one of the channels. Now I'm going to talk about a little bit of the coexistence of 802.11b and 802.11g. All right. So nowadays we don't have as much as we did in the past. These devices and these APs. Mostly nowadays we use 802.11n and AC, but there are some out there. So first we need to know how it works. So 802.11g are OFDM rates, and they are different from 802.11b, which is DSSS. So when 802.11g tries to communicate from between a client and an AP, 802.11b does not understand, and they might think that it's a noise, and there might be a collision because of that. So since we are trying to doing this communication, there must be some kind of coexistence, some kind of a way that both can understand each other. Because of that, there is a frame that is called request to send, RTS, and also a CTS, which is clear to send. So every time that when there are devices, mixed devices between 802.11b and 802.11g, they are going, first when they want to send a frame, they need to send first a request to send, and then when the AP gets it, receives it, and if you see, and they check if the channel is clear to send, and then the EP replies back with a clear to send. There can be also another way to do it, which is CTS to self. Okay, so this is another way to do it. So the CTS to self, it is where the client or the AP sends with the destination address with its own MAC address. Okay, so this is how we can do a coexistence between 802.11b and 802.11g. There are some limits, of course, because 802.11b is lower than 802.11g. So every time that an 802.11g tries to send something, it will first check if the channel is clear, and if it is, all of the other stations will wait for their time to send a frame as well. So every time that it sends a message, it sends a frame, 802.11b devices will stay quiet for a number of time, the duration value, it will stay quiet, and then after there is the 802.11g finishes its transmission, then the 802.11b can transmit. So because of this protection mechanism, it is good for 802.11b devices, but it's not so good for 802.11g, because when we only have 802.11g devices, the maximum throughput could be about 23 megabits per second, but when there is a 802.11b device, the throughput goes down to 8 megabits per second. So whenever you have a chance, do not allow your 802.11b devices to connect to your network unless it is some kind of a requirement that you need to have 802.11b devices. So today, OFDM modulation. So as you know, we have 20 megahertz bands. So inside of this 20 megahertz band, we have subcarriers, and there are 64 subcarriers, and each one of these carriers have a value of 312.5 kilohertz. So that's one of the things that you have to know. And there are some of these subcarriers are used for synchronization. And also, talking about protection for 802.11n, 802.11n does not repeat the same kind of weaknesses that the 802.11g has it. So first, they send a frame using the legacy speed. Legacy speed would be the mandatory speed, and then it sends the rest of the frame using 802.11n speed. So also, so we can have some kind of, when we have a mixed environment where we have 802.11a, 802.11g, and 802.11n, when, for example, when we have channels, when we have APs transmitting on channels 36 and 40 as a 40 megahertz channel width, and when there is a neighboring AP transmitting only on channel 40 in a 20 megahertz band, there might be some collisions. How does that work? So first, on the left side, there is the AP is trying to transmit on both channels, on both channels 36 and 40, and then when it hears a collision, when it hears that not a collision, but when it hears that the median is busy, the client, which is the B right here, we will only transmit on channel 36. It will not transmit on channel 40. So every time, this is the only, this is the protection that 802.11n has it. So firstly, it hears the channel. It hears if the channel is clear using CCA clear channel assessment. When it hears and see if the median is busy or the median is clear, it will transmit or will just hear as a collision. So when we going a little bit faster with 802.11n channel aggregation, 802.11n aggregates 2 carriers or more than double the speed. So instead of 64, we will have 128 subcarriers, and 14 of them are for calibration on the sides and on the center, and 6 of them are for synchronization and tracking, leaving us with 108 data subcarriers instead of 48. So for 802.11g on 20 megahertz channel widths, we would have a total of 64 subcarriers, and out of these 64, we would have 12 subcarriers for calibration, 4 subcarriers for synchronization, and leaving us with 48 data subcarriers, giving us 54 megabits per second to transmit up to. And when we aggregate 2 channels, we can have up to 119 megabits per second. So one of the new features that we have for 802.11n, the main one would be the MIMO, which is, and MIMO is multiple input, multiple outputs. And for example, one of the features that we have that uses MIMO and gives us more reliability during transmission is transmit beamforming. For Cisco calls it client link. So the emitter coordinates the signals sent on 2 different radios so that they reach the receiver at the same time. So which means is, let's think that this client is a little bit far away from the AP, and when it's far away, the AP senses it, and we'll try to give it a better throughput, a better data rate, so the network is not so slow, because the client is far away from the AP, so it sends two channels. It sends two signals on different antennas. So it can, when the client receives it, it will sense that the speed is a little bit better, and he can hear a little bit better what the AP is sending to the client. Also, we have our MRC, maximal ration combining. The receivers aligns a signal received on different radios. So it is one of the features that helps the client to have a better performance, to have a better data rate. So at the same time, the AP will send on different radios to the client. The client will hear it, and we'll see that it can improve its performance during transmission. Also, there is spatial multiplexing, where each radio sends a different information, and when it reaches the client, the signals will be combined. So the objective of this is to achieve extreme throughput gain. So, for example, you can send on one spatial string the letters A, C, and E, and the other stream will receive B, D, F. So in the end, you will get the information will get to the client faster than only having just one spatial string. Nowadays, we can have some APs already have 4 spatial streams, but the clients I've only seen up to 3. Most of the clients, smartphones and tablets, some of them have only 1 spatial stream. A few of them have 2 spatial streams, and also on laptops they also have 1 or 2, and just a few of them and have 3 spatial streams. And one of them that I know from the top of my head would be the MacBook Pro. So these MacBook Pros have 3 spatial streams for both 802.11n and 802.11ac. Going a little bit faster from 802.11n to 802.11ac, now we can have up to a channel width up to 160 megahertz. We have more spatial streams, up to 8, and we have a better modulation. We jumped from a QAM 64 to QAM 256. We can achieve a better throughput and achieve better speeds with it. Also, the new 802.11ac, it is in the standard, but when it came to the market, it came as waves. So wave 1, we only had 80 megahertz band and 256 QAM. And then when the wave 2 got to the market, it came with 160 megahertz band, and also with mu-MIMO, which is you can send to the AP will send to the client, to 2 different clients at the same time on the same frequency. It can send on different. It can send for 2 of them. So when it sends to the it's always downlink, so it's always from the AP to the client and not from the client to the AP. So and also they must be they must be far away from each other, not too near, so it will not work. The mu-MIMO will not work. So this is one of the features that mu-MIMO gives to the client, to the network. it uses the airtime a little bit better, but nowadays we don't have as much clients as we need to use this feature. So for now, I would say that MuMaImo is growing on the market, but it's not as it will take a little time to be more accepted to the market and send and sell more devices and clients. And the same way that we have protections on 802.11n and 802.11g, we also have a kind of protection on 802.11ac. So it uses the same logic as 802.11n. It sends the frame. The beginning of the frame is low on the highest mandatory rate, and then sends the rest of the frame on the using the speed, the 802.11ac speed. It does also have a protection against channel width. So in this case, for example, the AP sends an RTS in the air to this client. The RTS is in 20 megahertz format, but it indicates the 80 megahertz bandwidth. So when it sends it in the air, the client will hear it, but it only hears only on two channels out of the 80 megahertz band, because it has an interference. So when it responds back to the AP or clear to send, it will only reply back in a 20 megahertz band format, but it will indicate a 40 megahertz bandwidth, and then it transmits it sends the transmission the data. Now I'm gonna show the MCS index for 802.11n and 802.11ac. So we have the 20 megahertz column, the 40 megahertz column, the 80 megahertz column, and right here where my video is, it is the 160 megahertz column. So the orange one, it is for 802.11n, and the blue one, it is the 802.11ac. So as you can see, we have the data rates for not using short guard interval and using short guard interval. So the no short guard interval, it is a 800 nanoseconds, and the short guard interval, it is 400 nanoseconds. When we use short guard interval, it improves the data rates in 11%, but it may increase the retries due to echoes and reflections. It is only useful in good RF environments. In bad environments, it will make your network worse. And when we double the channel width, for example, from 20 megahertz band to 40 megahertz band, it improves data rates in 107%. For example, when we are transmitting on MCS7 for 802.11n, in 12 megahertz band using SGI, short guard interval of 400 nanoseconds, we can get, in just one spatial stream, we can get 72.2 megabits. When we transmit on 40 megahertz band, we can get up to 150 megabits. Talking about spatial streams, when we add a spatial stream, it improves the data rate in 100% in the same channel width. For example, in this case, we are talking about one spatial stream. So when we go to the table below and we see when we see two spatial streams, we can see that it doubles from, for example, from 72.2 to 144.4 megabits. And we also have the coding. The coding means that how much of the data stream is being used to transmit usable data. So, for example, in this case, on MCS 8 for MCS 8 and 2 spatial streams for 802.11 AC, we have here 3/4, so it will be 75% of this data that it transmits, it is usable data. Now I'm gonna show how the Wi-Fi works. Okay, so firstly, the client wants to send a frame. For example, let's think that the client wants to send a frame to an AP. So first, it decides that he wants to send a frame, and he needs to pick up a number and count down from there. So this would be the backoff timer. It is the initial number that you pick and count down from it. In this case, it chose 21, so it will count down 21, 20, up until 0. But in this case, this client here, down here, he got to the medium first, and he said, when he was sending a frame, he said that his duration ID, his duration would be 24 slots. So since this client here started to send, the other client that was counting down from 21 and he stopped at 18, he will need to recount again. With that, he's going to add 24 to its number. So it stopped at first, it stopped at 18. Now he's gonna add 24 to it, a total of 42. So he's going to resume the countdown from the new value, 42, 41, and up to 0. When it reaches to 0, you will see that the medium is free, and he can send the frame to the AP. When it sends and the duration time of this transmission, it will be the time to send the frame plus CIFS plus ECK. CIFS is short interframe space. It's the silence between unicast frame and its ECK. Acknowledge frame is every frame that an AP or a client sends, it must be ECKed from the other side. If it does not, it gets retransmitted. So then it transmitted the frame, received an ECK, and this is how it works. So right after the AP sends the ECK, the other clients that are associated to this AP as well, you will wait for diffs. Diffs is distributed interframe space. It is the silence between one transmission and the next, and it's basically calculated with diffs equals CIFS plus 2 times the slot time. So the slot time for 802.11 A, B, G, and AC is 90 microseconds, and the CIFS for 2.4 gigahertz band is 10 microseconds, and for 5 gigahertz band is 16 microseconds. Also, the contention window. The contention window, it is the window, how much the client will wait to send the transmission. So the contention window, when we were using DCF, distributed coordination function, it will basically all frames had a contention window minimum of 15, between 15 and 31, and contention window, the maximum contention window would be 1023. When WMM was released, frames could get marked with a up value, user priority value, and when the frame and when it is identified by a WMM compliant device, it will send the frame with a contention window minimum differently. So when a frame is marked as a voice, the contention window minimum is 3 and the maximum is 7. Video is 7, the minimum, and the maximum is 15. In best effort and background, the minimum is 15 and the maximum is 1023. So this means that whenever a frame wants to send, whenever a client or an AP wants to send a frame which has an up value, it will, the countdown from this number up to 0, down to 0, it would be less. So it gets a little bit, it gets the probability to get the medium free, the RF medium free, is higher for voice and video than for best effort and background. So that's why when we are using a telephone, an IP phone on a wireless network, there is a priority. This priority is kind of like, is when you have it is the probability. Actually, it is the probability. Is the probability that the telephone can get out the medium free is higher than any other kind of device. As I said, the user priority up values, it matches with the 802.11 and 802.11e up value and the WMM AC name. So for voice, the up value is 6 and 7. For video, the up value is 4 and 5. For best effort, it is 0 and 3. And for background is 1 and 2. So since this is a presentation that also focuses on design, when we are designing a Wi-Fi network, we need to have these 3 key things on our mind. First, we need to know how the clients hear the APs. So in a communication between the AP to the client, how the clients hear the APs. We can check that doing passive site surveys. This is how we see how the clients hear the APs. So, for example, when you're using your smartphone and you turn on your Wi-Fi, you can check how loud is the AP are transmitting its beacons from the AP to the clients. So when you turn on, for example, your Wi-Fi analyzer, you'll see the transmit power in dBm, for example, -50 or -67, 5, so on. So this is how the clients hear APs. You will one of the ways to see that is the passive site survey, not connecting to it. The other way, we also need to know how the APs hear the clients. So it's not a one-way transmission. We need to know that we are transmitting, the clients are transmitting to the AP, and the AP is transmitting to the client. So it's a two-way communication. And so we need to know how the AP, we also need to know how the APs hear the client when it's transmitting. So one way to check that is going on a controller and check what is the RSSI for each client, or you can go to management system, for example, Prime Infrastructure, that also has the same kind of information. And the last thing, we also need to know how an AP hears other APs, because think that there are 5 or 6 APs only transmitting on 2.4 gigahertz band. We only have 3 no-overlapping channels on 2.4 gigahertz band. So that's why we need to place the APs that are transmitting on the same channel far away. They should not hear each other too loud. So they need to be as far apart as they can. Of course, respecting the roaming and all of that. So we can check that using using the Prime Infrastructure, or even in a predicted design tool like Ekahau or AirMagnet. And we can also get the configuration and get the status of a wireless controller and use a config analyzer to check that. So it makes it easier for us to have it and see it, how each AP are hearing each other. Another thing that we have to take into account when designing a Wi-Fi network, it's the signal attenuation. So in an office, we have walls, tables, chairs, and other things that can attenuate the signal. And here is a guide. Of course, it depends on each material. So this is just an average. The best way to know for each design, the best way to know that what is the attenuation for each wall, for example, you have to do a survey with this and use your client on one side of the wall and the AP on the other side of the wall, and then you can move forward, like move ahead. You can move away around 3-4 meters away from the AP and from the wall, and then you can check how big is your attenuation from the AP going through the wall and then reaching your client. So here you can see a few examples with an average number, and that would be plasterboard wall with a 3 dB attenuation, glass wall with metal frame 6 dB, cinder block wall 4 dB, office window 3 dB, metal doors 6 dB, metal door with brick wall 12 dB. And most people don't know that, but you are also, you as a person also attenuates the signal. We are made of 77% of water, and water, it attenuates the signal as well. So whenever you're using your phone in your ear, your phone, your smartphone, or even your IP phone, whenever it depends on your position and it depends how you're holding your phone, you can lose 3 to 6 dB of the transmitted signal. So we also have to take into account when you are using an IP phone, and we have to take into account people. That's also how you design a network. Another thing that people don't know and which interferes on the Wi-Fi network is the client-induced interference. What is it? Think like this. Nowadays on a stadium, we have fans with smartphones. Some of them use the Wi-Fi network. They use the Wi-Fi infrastructure, but some of them, they do not. They just leave the Wi-Fi on their smartphones, and that also it also interferes to the actual Wi-Fi network that it's on that site, because even though they are not connected they are not associated to the wireless LAN, they are trying to connect to the known network that it is saved on the smartphone. They are always probe requesting and checking if their saved networks on their phones are available to connect to. So what does it look like? For example, right here we have the 2.4 gigahertz band, channel 1, channel 6, and channel 11. Right here you can see that there are transmissions because the Wi-Fi network is on and it's working. So you can see that on the 3 channels we have transmissions, and the RF medium is busy. And then they decided to shut down the wireless LAN infrastructure, and you can see that there are still transmissions. They are sending the clients are sending probe requests to each one of the channels. So it's always better to have someone associated and connected to your wireless network, because they do not probe requests as much as they do when they are not associated to a network. So this is something that we need to account for, the way that you allow your clients to connect to your network. The easier it is to connect to your network, the better. For example, you don't need to design a web portal, because this takes time, and clients sometimes, and the customers and the client and the fans, it takes some time. They do not like to put their information on it. So the better way to do it would be just an open network with no web portal, making it easier for the client to connect to the network. And one example of this is the iPhone 5S using iOS 7.0.3. It sends 4 probe requests per learned network per channel every 3 to 6 seconds on each one of the 2.4 gigahertz channels. So from channel 1 and 11, it will send the probe requests for each one of the learned networks. So if you have 10 learned networks on your iPhone, it will send a total of 40 probability requests per channel every 3 to 6 seconds on each one of the 2.4 gigahertz channels. So when associated, it does not send as much as probe requests as unassociated. So we don't have a lot of client-induced interference. Another thing that we have to make sure that we do on our network, on our wireless network, is to try to disable lower data rates. If you don't have to support any kind of 802.11b device in your network, just turn off the data rates of it up until 11 megabits. You don't need that. You don't need to support them because they slow down your network. So, for example, if you don't need to support them, just turn off up to 11 and set as 12 as mandatory, the lowest mandatory data rate. So nowadays, what I do is to set to 18 or 24 megabits, the lowest mandatory data rate, but it's up to the environment, up to your design. You need to check the customer requirements. So this is one of the things that you also need to take into account when designing your Wi-Fi network. Also, you need to think about antenna placement. In a high density, for example, in a high density environment, such as conference halls, the best way to design your network is using external antennas, semi-directional or even directional antennas, mounted on the top of the conference hall, and the antenna should be pointing down. So you can have smaller cells, and the frequency reuse will also be better because you can have more frequency and then you can add more capacity to your network. And so for conference halls, antennas, external antennas, semi-directional or directional antennas are pointing down are the best for this kind of design. It's not like an office. When we design an office, usually when you design an office, omni antennas are the best. With APs with omnidirectional antennas are the best with internal because they have the aesthetical to look good and not look very bad when you place it on the ceiling. So there are various kinds of designs. So for high density air environments, we should create small cells, and so we can reuse the frequency and add more capacity to the wireless LAN network. Okay, and that's it for today. I will post this video on YouTube, so whenever you have a question, I can answer to you. Okay, and I'd like to thank you for watching it. I hope you can get a better understanding of Wi-Fi and properly deploy it. I hope you have enjoyed. Thank you very much for watching.